Hello everyone, I'm Thomas again from the KTH team, and I will present to you problem number 5, popcorn. Let's start with the problem statement, or maybe with the emphasis of the problem statement. So the problem statement says that at a certain temperature, popcorn bursts open, jumps and emits a pop sound. And we are to devise a method to estimate the jump height based on measurements of the sound. So this is the essence of the problem. To produce a method to estimate the jump height based on the measurements of the sound. And the problem statement goes on to include some parameters, such as type of cornings, initial positioning of corn, heating mechanism, heating rate, and kernel country. But the real essence of the problem is to produce this method. So let's start with an example of how the popcorn actually pops. Here's a high-speed video of it. It's actually quite fascinating and really beautiful. This is taken from a research article published just a few years ago. We have our own example as well, with not a high-speed camera, but you get the idea. So before actually producing this if we're actually producing the measurement system and method, we want to know qualitatively about the system itself. For example, we need to know why does it pop, why does it jump, and why does it emit a sound. So to answer these kinds of questions, the natural thing is to turn to previous research. And this article that I mentioned is maybe the essential reading in this, because it talks about all different mechanisms in popcorn. There's also lots of other research articles about popcorn because people think it's a fun thing to study. And also there's commercial success in it, because if you optimize the size of popcorn, you can fill bags with less popcorn and thus make a bigger profit. But why does the popcorn actually pop? Not all types of corn pop, just popcorn. And the difference between them is that the pericarp, that's the outer layer of this, is harder. So what this means is that when water expands in this as it is heated, we get a higher pressure in it before it bursts open. And this happens at around 10 atmospheres. And it also happens at a critical temperature. This is also from the same article. On the x-axis we have temperature, and on the y-axis we have percentage of popcorn popped. So at around 180 degrees Celsius is the critical temperature where all popcorns pop. But why does it jump? The research article says that it's because of a leg that pops up and pushes it out. So here we have graphics of this. At this point we have a fracture. The leg starts forming out, and it pushes the popcorn into a rotation and a takeoff. And on the following pictures we see the whole trajectory. But here's something we must distinguish. What happens if the popcorn actually bursts open up here? Then it wouldn't jump. So if it bursts underneath, it jumps, and if it bursts on the sides or on the top, it doesn't jump. Now to the second part of this phenomenon, and it is the sound. And this is the really important thing, because the sound and the leg are not connected. And this is supported by this measurement from the same article. They have measured the sound at the same time as the fracture. And what they see is that the sound comes before the jump. It's not because of the contact of the leg with the ground. It's because of the high pressurized chamber that gets depressurized, producing some kind of shock wave. So what this means is that, together with the fact that not all popcorns jump, but they can still make the same sound, that there should be no global correlation between the height and the sound. But maybe if we filter out the ones that burst underneath, we can actually devise the system that this problem asks us for. So from life experiences, when you get popcorn, and some popcorn, and sometimes you get it in your face, it never happens silently. So there should be some kind of relation. And this can be formalized with an energy argument. The total energy must be conserved. So the energy stored in the popcorn from the heating should be equal to the energy in the sound, energy of the speed in the x direction, the y direction, the rotational speed, and other losses. But we will argue that only the y direction is important, that other ones are negligible. Furthermore, this is maybe the most important assumption we do, is that the total energy stored is proportional to the sound energy loss. So based on these two assumptions, we can do some calculations. The sound energy is just intensity times area times time, and intensity is can also be expressed in this way. The area is taken as a sphere, and the energy in the y direction is the potential energy at the highest point of the trajectory. So given these assumptions, we get this relationship, that the height is related to the amplitude max of the sound signal by squaring this and multiplying with this factor. So our hypothesis is that the sound, these are our assumptions, and based on the assumptions we have, there should be no global correlation, but by filtering out the ones that burst underneath, we get a linear relationship between the height and the square of the maximum amplitude of the sound. So to test this, we have this following setup. Here we have a 240 FPS camera. We have a hot plate. We have a separate microphone and a ruler to see how high it pops. So this is an example. Here it jumps. What does it jump? It jumps 28.3 centimeters. So this is a quite high jump. For this particular jump, we have the following sound signal. So what can be noticed here is that the sound signal is very large at the top. So our theory only looks at the maximum, and because all other signals are very low, it's quite possibly a good way to describe this. Moving on, by extracting all the maximum amplitudes from the sound signals, we get the following. On the y-axis we have the jump height, on the x-axis we have the sound amplitude. Notice that the sound amplitude is in arbitrary units, because the microphone does not pick up an absolute sound pressure. It normalizes to some kind of interval, and it's also dependent on the sensitivity of the microphone. But relative to each other, we know how they relate. But moving on, going back to the fact that not all popcorns actually jump. Some burst on the side. So here we have a picture of a popcorn, and here it has burst on the side. It has emitted the sound, because the sound isn't connected to the actual jumping mechanism. But we can't estimate the height of it, because there is no height. And of course, there's also the few popcorns that don't pop, unfortunately. But we have the ones that do pop. So by filtering them out, we get the following three parts of our data. On the x-axis, we have the ones that burst on the side. In the center of the coordinate system, we have the ones that do not pop. But here we have a relation between the jump height and the sound amplitude of the ones that actually do pop. And this seems kind of bent. It's supposed to be a quadratic function, and it seems so. But to actually test this, it's easier to plot it. Yes, this is our relation. To test this, it's actually easier to plot it this way. Here we have the amplitude squared against the height, and we do a linear fit. The problem with our method is that we can't estimate k in the conversion between the sound energy and the total energy. So we must do a fit. But this is the kind of relationship that we should use to answer this problem, that we can estimate the jumping height based on the sound. Thank you.
I heard in the presentation, first we saw a video demonstration of the phenomenon. He went on to a qualitative description that was mostly based on a literature review. He talked about conditions for jump occurring in the kernel, as well as the actual physical source of sound. He then made an energy argument to form a relationship between the jump height and the sound amplitude. So things that I enjoyed about the presentation were, first of all, the demonstration and the qualitative understanding of the phenomenon, which I think is really important to ground our understanding of what we're talking about. He talked about some critical values for this phenomenon to occur, which gives us a sense of scale. 10 bars, so for fracture of the kernel in terms of internal pressure. He gave us evidence of his experimental setup and some nice experimental results to try to confirm his theory. However, some points that I like to start to address in the discussion is that in particular in his experimental results he was somewhat selective in the points that he included and wasn't able to create a rigorous method for quantifying what he considered a downward jump. So in some sense, I feel that this prevents us from making, or the problem asks us to make a prediction about the jump height based on the sound. And so it's hard to make a prediction when you're just trying to fit the relationship to selected data points. I'd also like to discuss a little bit of stronger justification for why the sound energy is proportional to the total energy. And maybe have some discussion about how varying the kernel parameters could affect your experimental results and how you think it affects the phenomenon, because we had some parameters specific to the popcorn that were mentioned in the problem statement itself. So that sums up my overview of the report, and I'd like to move on to the discussion.
Okay. Good.
So I guess first of all, I'd like to address or go back to projecting the downward jumps that you observed in your experiment, and sort of your methodology for that, how you can justify that using selective results would allow you to make a prediction. So if you can speak to that first.
Yes, the important thing to note here is that it jumps because it uses a force on the ground. If the force is produced in the area, it doesn't jump. So we have to, in some way, filter out this. We have filtered out it manually. Of course, you can build a technical system to do this. You could place the whole setup on some kind of scale and see what the scale reads, but this was an easier way for us.
Okay. And how, were there any kind of edge cases where the fracture occurs, not directly underneath the kernel, but would produce some very small jump that you're not able, that's not clear to see?
I can show you some edge cases in my presentation. So notice that on the x-axis we have blue points. But we also have some blue points that are slightly above the x-axis. We estimated that these actually burst on the side, but the expansion on the side makes them go up, but they don't jump. At the same time, we have those that do jump a bit. They burst underneath, but they also have the same height.
Would you agree that there's sort of some fuzziness between it jumping and expanding on the side and excluding that from the
yeah, of course there's some kind of fuzziness, but it's two distinct things that happen, and when the two distinct things turn into each other, of course there's some kind of gray area.
Okay, great. And so you still think that your results are statistically significant?
Yes, if we look at that relationship, it fits quite well.
Okay.
Not perfectly.
I mean, yeah, you just also have quite a few data points. Or do you agree with that?
I agree with that.
Okay, great. And then just to move on to another point, in terms of influence of other kernel parameters, if you were to include them in your experiment, can you speak briefly to what you think the effect of the kernel positioning would be, parameters like the size, shape, and thickness of the shell in the kernel?
Yeah, if the shell is thicker, it will withstand a much higher pressure. But so when it actually releases, the pressure will be higher. So both the sound should be higher and it would jump higher. But the actual basis of the assumption of this will not change. So even if the kernel is thicker, the same thing will happen. Do you agree?
Yeah, I agree that we will see the same phenomenon if the burst occurs below the kernel, such as to propel it into the air. And what about kernel positioning?
Kernel positioning. I guess this is easier to draw before. If we have some kind of heating source, a hot plate, most hot ones are quite flat. This is slight acceleration. But when you heat them here, this part will be heated more. If you position them in this way, this part will be heated more. But this is kind of the naturally occurring situation.
Right, and would you agree that the thickness of the kernel isn't uniform, so the positioning could also affect where the fracture occurs?
Could you repeat that?
That the thickness is not uniform around the kernel.
Yeah, the thickness is not uniform. So.
And also, as we're speaking about the hot plate, what do you think the effect of your choice of the heating plate has, for example, the heating rate and so on?
I'll bring up a slide about that, slide 38. So there are actually lots of heating mechanisms that can be chosen, but the hot plate is chosen because of these measurements. So you are specifically about the heating rate.
Mm-hmm. And how that influences the phenomenon.
Yeah, it only starts heating below. If we were to have some kind of reflection, some kind of area that reflects the heat, it would be heated more uniformly. So then it's more probable that it bursts on the top. But the actual mechanism of bursting remains the same. So the assumption should still be valid.
Okay, thank you. I agree. And just in our last seconds, could you give a brief statement about energy losses in the system, or where energy goes besides jumping? And so on?
Yeah, it also goes.
Sorry.
Okay, so now the reviewer has 2 minutes to ask questions.
Okay. Please answer me the questions as follows. First is, could you give me an explanation to the to the coefficients of the K in your presentation?
Could you repeat it?
Could you explain the coefficient K, the coefficient K?
Okay, so K is a proportionality constant that transfers the sound energy to the total potential energy in the popcorn. So it's dimensionless.
So what's the physical meaning?
It's dimensionless. It's just a proportionality constant that translates this energy to this energy.
Okay. And any other parameters could you consider in your experiment, such as a type of the coin and the heating rate and current coupling?
We haven't specifically looked at the other parameters, but the method should remain valid because the assumptions remain valid in all those cases.
Okay. And do you determine the limits of the precision in your choose method?
What was the last word?
The limits of precision.
Yes. So we had my fit, and at most it was 2-3 centimeters from the actual value. So that's the limits of the precision.
So to the opponent, do you think the K has this physical meaning?
But you already have 1 minute.
Okay. Okay, hello everyone. My name is Ma Huiying. I'm presenting the team of China to give a review representation. Okay, this is a problem. And it stands for the reporter, and the opponent gave a nice reporter. And let's first look at the summary. The first to the reporter, she explained the why and how the kernel pump and jump, and then he discussed the influence of the temperature, and also provide how the pump to make the sound and the property of the sound. Also discussed its energy conservation. And finally, he said experiment to observe its motion and relates to the sound and get the graph to the coincide with the theory. And to the opponent, she gave a nice report, and she could make the further prediction of the explanation to problem, and also consider the energy losses. And also find some problem from the reporter, and also consider the condition of the kernel, and the heating tools should be explained. So the next I will say something about the pro and cons. The first to the reporter. To the reporter, he gives a reasonable explanation of the phenomenon of the popcorn, and also give very details information about how the popcorn burns and emits a pop sound. And but actually, he has a lot of problems. For example, he studied importance of the other main parameters and didn't consider initial angles of the jump, and also could not consider the other typical parameters. So to the opponent, she provided an appropriate model. And did not find out the main parameters. This is our discussion point. The first is is there any other parameters we should consider in this problem? And the other is how to improve this setup. And the third is how to relate the pump sound and the jumping head. So, to the reporter, could you discuss about the first question? Okay.
Yes, the problem statements ask for lots of parameters to be varied or at least put upon, but the assumptions we do remain valid in all cases. So the whole thing should remain the same.
Okay. Do you agree with these ideas?
Yeah, I agree that we can make these assumptions in this case. I think that it's interesting to consider the effects that other parameters might have, such as the heating rate parameters relating to the kernel but we can start to describe the effects of those qualitatively in this case. And I guess kind of in that same vein, I had another question for the reporter, which was that you said there are some cases where there was no pop at all. And I was wondering why you think that's the case and how that might depend on the parameters of the system.
Well, it's completely natural. If you pop popcorn, there's always the ones that do not pop. So that could be because of that they are very dry, so there's not any water inside of them. It could also be because of that they are already punctured in some way, so they can't be any vapor buildup. So it's completely natural.
So, okay, and I think maybe you should not consider another important parameters is the initial angle of the popcorn.
I want to show some calculations on that because I think it can answer a question very well. To come up really soon. So the initial angle, what the initial angle does is that the popcorn maybe doesn't jump completely high up. So we get energy losses to the horizontal movement and the rotational movement. So the energy in the rotational movement can be calculated through this expression, and by actually measuring the rotation rate, we see that the quotient between the energy rotation divided by the actual energy in the upwards direction is less than 1%. And in the same way, for the x direction, it's also very small. We consider it a parabolic motion, and we see that in the worst case, when it jumps as long as it jumps high, this is quite reasonable from personal experience, the quotient is below 6.25%. So we have no energy losses. So we don't think it's important.
So, did you observe any cases in the middle of that regime between the most extreme jumps and the jumps that you just counted?
Could you repeat that?
Did you observe any jumps that fell in the middle of that regime to the most extreme jumps and the lowest jumps? And is there a region within that regime where the rotational energy or the energy in that direction is not negligible?
If we bring up the plot again, or maybe not this plot, actually this point has a higher rotational energy than the rest of the points.
Okay, all team members can join the discussion.
This means that it should be below the prediction, but it's actually above the prediction. So it doesn't seem to affect it very much.
Since a large portion of the problem dealt with predicting the height, why did you not choose to use your model to perform predictions?
We interpreted the problem as to devise a method. What we have done is exactly to devise a method. By using this kind of fit with this relationship, we have devised the method, and we can do predictions for other jumps after we have done the actual calibration curve. And the reason why we can't do real predictions is because we don't know the transfer from the total potential energy in the popcorn to the sound energy. Of course, you could look at that theoretically. It's some kind of chamber that expands. But the problem here is that there's lots of theory for this, but only for perfect resonance chambers, where we have harmonic frequencies and so on. But this problem is much more chaotic, so there is no easy transfer function. That's why we assume the linear relationship.
I understand that there's a large amount of stochasticity in the problem. I just figured it would be satisfying to see some predictions based on your models.
Yeah, we can make predictions based on this after we have done the calibration curve.
I have two questions. One, going back to the slide you just were with your proportionality relationship. Is your proportionality constant the same between different trials, like the same for each kernel?
Do you mean this? Mm-hmm. Well, it's not the same. If we would fit a line between this point and this point, it would not be the same. That's why we use lots of points to get a better spread between the errors and get a better line at the end.
So, in your research, the object is the popcorn which jumped vertically.
Yep.
Okay. And other team members have some questions? Okay. You can ask questions.